through profiling, we found that our example code was spending almost all of its time in the function spring force. So this is a natural target for optimization. In this video, I will show you how to make better use of numpy to enhance that efficiency. So we want to numpify the function spring force even more to enhance the performance in that way. And as we'll see, it can actually be quite dramatic. So just as a reminder, where did we start from? So let's just run this simulation again to have a baseline. I'm timing this simulation again, and if you look closely, you see that now I'm using the cell magic time it. Now time it is a little bit more accurate than just time, because it typically runs the code several times to average, so it can be, it can give a bit more accurate estimation of how long something runs. That's especially important if we have code that doesn't run for so long, so actually very short times, because otherwise you could have some quite big measurement uncertainties. But we'll see that later. So here we see, again, well, the code took approximately 3.4 seconds. So let's see how much we can improve that. To optimize our code, we will now rewrite the spring force function. And I have copied here the original implementation of the spring force function in this cell. So we will use the spring force function. First of all, we're going to copy the code here, because we use that then to line by line rewrite this in a more numpy optimized way. But having this function, this original function, actually serves two purposes for us. First of all, it sets the baseline of how much more efficient we can get. So we can compare the speed of the new function to the old function and see if we actually do get any better. But it also serves as a reference with which you can check the correctness. Because you see, when we are rewriting this function in a more efficient way, we could of course easily introduce an error, and then our code would be wrong. So if you optimize your code, it's always important to keep correctness, of course, into account. And the most easy way that we can do is we can compare the output of the new function to the old function and see if they actually agree with the numerical accuracy. So, so we need to run this spring force function. So we need the function, but we also need some input data. It takes the positions of the balls. Now, I'm not actually taking a real simulation input here now. I'm going to just use a random matrix of the correct size. So this is often a good idea to do, because then you have just some random input, and it's not so likely that maybe you're missing something because your input is very special. So we're choosing here a random matrix of size n by 2. N was the number of balls, 2 was the number of coordinates, as our input data. And now we're going to time the original function to see how fast it is. Okay, we're using time it again. Here, the runtime of just one call to spring force is about 1.7 milliseconds. So here, time it is really essential to get a somewhat accurate timing here. So you actually see that it ran 100 times. Now, let's give a shot at optimization. So if we look at this original function, I mean, it's kind of obvious that the natural point for optimization is to get rid of this loop here. The general rule of thumb is you always start with the innermost loop. Well, here is actually just this one loop, so that's what we're gonna try to optimize. Note that we have been using numpy functions before, actually. So here, this expression is actually a numpy expression which is acting on vectors of size 2. But that doesn't give us as much speed up as if we could do that actually for all the coordinates, all the balls at the same time. So this is what our goal is. So let's copy the contents of the function, of the old function in here. So we want to get rid of this loop here. So let's take it out immediately, and let's right away unindent this by one level, so we want to have an expression without a loop. So when we want to write things in a numpy way, then the way that we're doing it is that we want to act on all the expressions in one go where we before had a loop. And in this particular case, if you look at the distance vector, what we're doing is we're taking the coordinate of ball I and we're subtracting the coordinates of the ball which was just one before. Now we can actually write down all the coordinates of all the balls in one go in this way that we use slicing of our array. So what we actually want to use here is we want to go from index 1 to 1 before the last index. That is because we wanted to include the first and the last ball, and this is the way how to write it. And from this expression, we want to subtract the coordinates of the balls that were just one before. But if they're one before, it means that you don't start from 1 and go to the one before the last one, but you can actually start from 0 and you go up to 2 before the last one. Yeah, so we just write it like this. So this is very natural to do this in numpy, and in this way we get all the distance vectors in one go. So we can get rid of this part here. Okay, so this is already done. This was very simple. Now we also want to compute the absolute value of the distance, for which we were using this expression down here, where we had sum over the distance vectors, the coordinates squared, and then taking the square root of that. Now if we were to use that expression here in the same way, what would happen is that it would not only sum over the coordinates, which is what we want, but it will also sum over all the balls, because now the distance vector is a n by 2 matrix, or actually n minus 2 by 2 matrix. And NP sum by default sums over all the entries. However, there is a very useful keyword for NP sum, which is the axis keyword, where you can say, well, only sum over a certain dimension. So this is axis, what we have here. And what we want to do is we want to sum over, in this case, the second dimension, which in Python notation has index 1. Yeah? So axis equals to 0, that would be summing over rows, so that would be summing over all the balls. But now we want to sum over all the coordinates, and those are in the columns, and this is written down here with axis equals to 1. Now then it's about doing the force calculation using distance vector and the distance. Now first of all, we have to again here only calculate the force between the ball with index 1 and the ball before the last ball. So we again do 1 to minus 1. And then we have this expression here, and that looks like it should actually work. So let's just try it like this. And let's move to the next ball. So this expression actually looks like it should actually work when you work with numpy arrays. Now, if we go to the next ball here, well, we actually know that we have to do the same things as we were doing before, but now we do not do the previous ball, but the next ball. So here we just write position pos 1 to minus 1 minus position from now starting from ball 2 until the end. And again, here for the distance, absolute value of the distance, we need to specify the axis keyword. Okay. And again, here we need to put in 1 to minus 1. So let's see if this works. So this was our first try where we were only using very simple numpy operations such as slicing and this axis keyword to the sum. Now let's try it on the input data, and we actually see it does not work. So why does it not work? Let's have a look at the error message. And it says, well, there's an error occurring in this line here where we are calculating the forces, and it says operands could not be broadcast together with shapes 48, so there was a vector of shape with length 48, and a matrix of size 48 by 2. And if we look at this, then we realize, well, we had here the distance vector. So it's an array of distance vectors. So this is the 48 by 2 matrix, n minus 2 times 2. And we have here the vector array of the absolute value of the distance, which is a vector of size 48. And indeed, that numpy cannot do. We know that if you write an expression like this with the multiplication or the division operator, the numpy will try to do operations element-wise. So do the same operation for every element of these different arguments. But here it just doesn't work because one is a vector and one is a matrix. So how can we go beyond that? There's not different ways of how to solve that problem. What we need to get at, we need to get to operands which have the same shape to be able to do these numpy operations here. And what's the common and the most natural way to do that is to use a numpy feature called broadcasting. Now this broadcasting can look a bit like black magic, but if you understand it, when you understand it, you actually see that it's not that hard. So I want to first show you how it works on a simpler example. So what is broadcasting? Well, we know that numpy can do element-wise operations on arrays when they have the same shape. So when there is an element-wise operation being done with two arrays, then numpy will do that if they have the same shape, or when certain other conditions are fulfilled. And this is then called broadcasting. And the rules are, in a nutshell, what I cite here from the documentation. So when operating on these two arrays, numpy compares their shapes, so their dimensions, dimension by dimension. And it starts with the rightmost dimension and works then to the left. And numpy says that two dimensions are compatible when they're equal. Well, this is what we already knew, if the shape is the same. Or if one of the dimensions is 1. So if you have a dimension which is a different value from 1, and one has a dimension 1, then numpy still does the operation. And for the dimension of size 1, it simply repeats the value to fill up the array such that it fits with the other size. Okay, so this is what broadcasting does. Let's look at this in a very simple example. So what I have here is I have two arrays. I have one array which is 3 by 2, and we have a vector which is of length 3. I'm defining that here. And we know already that if I want to multiply these two together, it does not work. That's the same situation as we had before. Operands could not be broadcast together with shapes 3, 2, and shape 3. So what you see is that numpy will look at this and say, well, there is no dimension which has size 1, so I cannot apply these broadcasting rules. So what we need to do is we need to make sure that this vector b, which is now a vector of only a single dimension 3, we need to turn that vector into a 3 by 1 matrix. Because if this is a 3 by 1 matrix, then numpy will use the broadcasting rules to make it in a 3 by 2 matrix by just copying the columns. Now there's different ways of how you can turn the vector b into a 3 by 1 matrix. You could use numpy reshape for that, or one can use the syntax that I'm showing here with mp.newAxis. So what you can do is you can write here the square bracket and then the colon operator for all the elements. So in principle, b has just one dimension, so it should be originally, it's just b like that. That means all the elements of b. But we can insert a new axis of size 1 by writing it in this way, that we write comma np.newAxis here in these square brackets. So let's have a look at this array that we get. So if we do it, then we see that the array that we get is now not longer a vector of size 3, but it's a matrix of size 3 times 1. And we can also see that output here now is that we have a matrix where the vector is one of the columns of this matrix, or the only column of this matrix. Now, just a note, sometimes when you look into code, you actually see a different syntax because mp.newAccess is actually equal to none. So you can also see that people write, instead of mp.newAccess, they just write none here. That works just as well. Personally, I feel that mp.newAccess is more explicit. So it leads to clearer code. And with that, we can now write our multiplication. We can write a times b with this new axis inserted. And we get a result now. Now, let's just think again. Just make ourselves completely clear what broadcasting does here. Huh? The dimension that is of size 1 now is the number of columns of b. So this is what we have here. And what the broadcasting does is that it just repeats this column here to get to the same shape as the shape A, which has 2 columns. So explicitly what we have is that this expression that we have here is equal to this expression. So where we multiply A with an array of size 3.2, where we have the same value in each column. And that does exactly that's then the trick of multiplying every row of the matrix A with the corresponding entry in the vector B using broadcasting. With the knowledge of numpy broadcasting that we now gained, we can now write a version of the function spring force that actually works in a completely numpified way. So let me first copy here again the code that we just wrote. It didn't work. And we know that the problem was in this line here. And the problem was that this is a matrix, and this were vectors. And what we actually wanted to achieve is that we wanted to multiply every row of this matrix here with the corresponding entry of these arrays here. And this is exactly where you can use the broadcasting, like I showed you before in a simple example, also here. So what you need to do is we need to make these arrays, these one-dimensional arrays, into a matrix, into an n-2 by 1 matrix. And we do this again with the same syntax as we had before. We add a new axis here. Now, let's write this in a bit nicer way. Bring this to a new line. And we also need to do the same as what we're doing here with the distance vector, with the array of absolute values of distances. And yeah, we need to do the same also for the other force. Okay, now let's see if this works and if it actually gives the same result as the original version. So I was doing this live, so you know I could actually have made a mistake, so it's always good to check that. Now I'm comparing numerical data, and you know the implementation here are slightly different. So typically you shouldn't compare the output of different numerical operations really bit by bit, so really exactly, because because of round-off errors there could be small differences up to machine precision. So for that there exists this function called mp_all_close, which checks whether a vector or matrix and a numpy array, if 2 numpy arrays are similar up to machine precision. So let's actually try. Let's run it, and we get true. Yeah, so the original spring force function, the new spring force numpy function, gave really the same result. So that's encouraging. Then now let's see how much of a speed gain do we get. So it's timing it. And we see here we get now 60 microseconds. Now if you remember what it was before, it was about 1.3 milliseconds. So this is, quite a significant increase in speed by more than a factor of 20. And if you look, we didn't actually do a lot of work. We just were using some concepts of numpy, which are quite general and which you can apply to very many different situations. Now finally, let's just put it all together again and do the full simulation. Now we know that, SpringForce basically took all the simulation time, so we expect, the same kind of speed up also here for the full simulation, but it's always good to just double check, right? Maybe we also overlooked something here. But what we expect is again a speed up of 20, of order of 20 or more. So let's see if this is actually true. And wow, well, we see here we find that our simulation now takes 170 milliseconds, what used to be 3 seconds. So it's actually a speed of around 20 or 30 compared to original version. Now this is quite significant, and we only spent around 50 minutes for doing that.